Welcome, learners. My name is Mr. Loyola once again. Welcome to Black Slides Online Secondary School. This is the platform where you learn the sciences, namely physics, chemistry, biology, mathematics, and the other on-demand subjects such as English, history, life skills, and others. Today we have the privilege of going through 2026 Loyola Jesuit Secondary School mock paper. This happens to be Physics Paper 1. It's a privilege to us. So let's go through the paper together without wasting much of your time. Stay with me up to the end. It is going to be helpful if you subscribe to the channel and hit the notification bell so that every time I upload a new video, you become the first to know or the first to see it. We don't have much time on our side. Let's utilize as much time as possible to revise as many papers as we can. So revise with me this paper from Loyola Jesuit Secondary School mock paper. Welcome, learners. The paper is meant to last for 2 hours, but we'll see, depending on how we control our pace, how long it's going to take us to complete it. Welcome, learners. My name is Mr. Loyola once again. So without wasting your precious time, let's go to question number 1. Question number 1, define the term electromagnetic wave. Electromagnetic wave is defined as a transverse wave made up of oscillating electric and magnetic fields that can travel through a vacuum. In other words, they are waves that can travel in a vacuum independent of material medium. Number 2, describe the relationship between the frequency, wavelength, and the energy produced by electromagnetic waves. All right, so frequency, remember, is the number of complete oscillations made per second. And the wavelength is the distance between adjacent parts of a wave which are in phase. All right, so these terms, these concepts or properties of waves are related one to another. So the examiner is asking us to describe that relationship. So the first relationship is between frequency and wavelength. You are familiar with the equation. You're familiar, I believe you are familiar with the equation V equals to F times lambda, or speed of a wave is equal to the frequency of a wave multiplied by its wavelength. All right, we can rewrite this equation as F equals to V divided by lambda, or speed divided by wavelength. If we keep the speed V constant, if V is kept constant, it means that F and lambda are related, but then the examiner is asking us to describe that relationship. So if V is constant, It implies that it entails that frequency of a wave is inversely proportional to its wavelength. Or if you want, you can say wavelength is inversely proportional to frequency. Inversely proportional to its frequency. So what this relationship means is that if we increase frequency, then wavelength becomes very, very small, decreases. The higher the frequency of the wave, the smaller the wavelength of that wave. So that's relationship number one, relating frequency and wavelength. Welcome, learners. So what the examiners are looking for from you is to say that frequency is inversely proportional to wavelength, meaning that as frequency increases, wavelength decreases. If we increase frequency, wavelength will become smaller and smaller. The condition here is that the speed v is constant. Remember that electromagnetic waves travel at a constant speed of 8 times 10 to the power 3 times 10 to the power 8 meters per second, or 300 million meters per second, if you want. All right, so that's relationship number one mark. Another relationship is to do with frequency and the energy. Frequency and the energy are related in a way that when the frequency of a wave increases, the energy that is propagating or transmitting or transferring becomes high. So we are saying energy of a wave, electromagnetic wave, is given by what is called the Planck's constant multiplied by frequency. If we keep this constant, the Planck's constant, then energy E is directly proportional to, written like this, directly proportional to frequency F, meaning that the higher the frequency of the wave, the greater will be its energy. That's what that means. That's the second relationship. All right, so energy is directly proportional to frequency. Therefore, higher frequency waves have higher energy, while lower frequency waves have lower energy. 2 marks, 1 mark for each of the points. Welcome, learners. Let me know where you are watching this from. Where are you watching these revisions from? Kindly text me on my number and say what you think about these revisions. Welcome. We are revising a paper from Loyola Jesuit in Kasumu. Welcome, learners, once again. My name is Mr. Paul Chilola, your teacher. Question number is about a ticker tape. This is a paper called the ticker tape. It's being pulled by a trolley through a timer, ticker timer. So the scenario is like this. Let me show you what's going on here. What's happening here is that you have a trolley. A trolley is simply something like a small movable object. It can move. It can be made to move in a certain direction. Let's say it's moving to the right. So to this, there's a paper which is attached. Attached to this, to the trolley, is a paper which is called the ticker tape. All right, so we have a paper which is attached to the trolley. Let's say this is a paper. And the paper is passed through what is called an object called the ticker timer. A ticker timer is simply a vibrator, an object that vibrates, and as it vibrates while the ticker timer is moving this way, while the trolley is moving this way, this direction, it's going to, the paper will also be moving along with the trolley, while the ticker timer is vibrating. So as it vibrates, it will leave a trace of dots on it. Right? So this is a trolley moving to the right, and then we have a tape which is passed under a timer. So this is timer. It's important that you know these things. Welcome, learners. So that's the scenario here. So as the trolley is moving this way, it's pulling the paper along with it, while the timer is vibrating. This sharp pointed end here has something like a pencil, sharp enough to make dots on the paper here. It's these dots that you see on the diagram. So we are asked to describe the motion of the trolley if its frequency is 50 hertz. So what does 50 hertz mean in this context? The 50 hertz given here simply means that it makes 50 dots. It means 50 dots. Sorry. This means 50 dots per second. That's the meaning of 50 hertz. Means 50 dots per second. That's what is meant by 50 hertz. It means that the ticker timer, will make 50 dots per second. So that being the case, then we can calculate the time taken for one dot. So time taken for one dot is going to be equal to 1 divided by 50. It's like we are trying to find period from given frequency. So dividing 1 by 50 will give you something like 0.02 seconds. What this means is from the first dot to the second, the time there is 0.02. That's what that means, 0.02 seconds. All right, that's what this means. To move from this dot to the next one here, the time will also be 0.02. Where is the 0.02 coming from? It's the time taken to make one dot from here, from this calculation. We are using the 50 hertz that is given. That's what is important to note. So therefore, the time taken for the distance of to cover 4 centimeters, the time taken will be 0.02 multiplied by 2. Multiplied by 2. 2 because there are two intervals here. You need to understand this very well. There are two intervals. There's this interval 1, then interval 2. The time to cover one interval is 0.02 seconds. So the time taken to cover two intervals is going to be 0.02 seconds times 2. That's why we are multiplying by 2. So this will take 0.04 seconds. 0.04 seconds. So from this we can calculate the speed between the first and the third dot, or for this interval here, the speed is going to be the distance covered. In this case, distance is 4 centimeters. 4 centimeters divided by 0.04 seconds. So when you divide this 4 centimeters by 0.04 seconds, you find that there is going to be, the result you get is 1. Okay, because this one, 4 centimeters in meters, is 0.04 meters. We are converting the centimeters to meters to divide by 100 there. So we shall have 0.04 meters divided by 0.04 seconds. This will give you 1 meter per second. Very small. 1 meter per second. So the speed of the ticker timer, the speed of the trolley for the distance of 4 centimeters is 1 meter per second. So 1 meter per second, this one. We need to do the same for this part here. For the second part where the distance is 8 centimeters. Where the distance is 8 centimeters. All right. So once again, it is important to note that from the first dot, from the end of 4 centimeters to the next, this is again the time taken there is 0.02. So we have 0.02, another 0.02, another 0.02, that's between dots, another 0.02, another 0.02, up to the last dot. Another 0.02. So the total time taken for the distance of 8 centimeters, total time is going to be 0.02 times 4. 0.02 times 4. Take note here, many candidates confuse the distance with the number of dots. Here we have 1, 2, 3, 4, 5. 1, starting from counting from here, 1, okay, 1, 2, 3, 4, 5. We have 5 dots, but there are 4 intervals. The number of intervals, these ones, is equal to the number of dots minus 1. So we have 4 intervals here. So the time taken is going to be 0.02 times 4. 0.02 times 4 is going to be equal to 0.8. It's going to be 0.8, I think.
Oh my goodness, you are absolutely right.
All right, so this will give you 0.02. This is 0.02 times 4. That's 0.08 seconds. So for which we can also find the speed. So the speed is going to be 8 centimeters, which is similar to 0.08. 0.08 meters. Meters divided by 0.08 again, seconds. Which gives us, once again, 1 meter per second. So since the speed in both sections of the journey is the same, that means the object, in this case, the object is accelerating with constant speed. So the object is moving with constant speed. In other words, it's not accelerating, it's moving with constant speed. Because the speed in the 4 seconds, 4 centimeter distance is equal to the speed in the 8 centimeters distance. So it's moving with constant speed. Moving with constant speed. Yeah, so welcome learners. My name is Mr. Loyola once again. It has taken us quite a bit of time to analyze this question. So in your response, make sure you say that since the speed in the 2 sections is the same, therefore it moves with a constant speed. And this is why the dots are spaced further apart, but still equal speed. Or rather, the dots are spaced same way, meaning that the spaces between dots are the same, implying that the body is not accelerating, it's moving with uniform or constant speed. So both sections have same speed. That means the trolley is moving with constant speed all the way. All the way. Make sure you are able to analyze these questions involving the ticker timer. They tend to be confusing for some students. So same speed all the way, constant speed all the way. As a matter of fact, the question would have been maybe 4 marks because you need to show all this working and then conclude accordingly. Welcome. Question number 2. Question number 2 is about liquid pressure. All right, so explain 2 properties of liquid pressure. That's very, very important. Okay, Remember that when you place a liquid in a cylinder, a liquid such as water, for example, the liquid is going to exert a pressure on the bottom of the cylinder due to its weight. And that pressure is going to increase as you go deep. That alone is a property. So let's imagine you have a tall plastic bottle like a cylinder or any other tall bottle filled with water. Suppose you make 3 holes, small holes on each side, okay? One near the top, the other one in the middle, and the other one at the bottom. You'll notice that when you put water in such a bottle, the water from the top is going to flow out only a short distance, and the water from the middle hole goes a bit further than that. But for the bottom hole, the water is going to be seen to shoot out the farthest distance and the strongest. That means that liquid pressure increases with depth. All right, so what I've just said can be shown. Suppose we have a liquid like water with 3 holes on it. With placed in a container that has 3 holes on it. So this is water. When the holes are open, water is going to come out of the holes of the container through the holes. Very important to note. So water will be seen to come out of the first hole, the one on top. Let's call this hole number 1. All right, let's call this hole number 1. And this hole number 2. So water from the first hole, the one on top, is going to come out covering a short distance. But water from the second hole will go a bit further than the first one. While water from the third hole, which is at the bottom and at much deeper level than 1 and 2, is going to go farthest. This shows that liquid pressure increases with depth. That's property number 1. So just say liquid pressure increases with depth, implying that the deeper one goes, the deeper you go in a liquid, the greater the pressure. The deeper you go inside the liquid, like water in a tall bottle, the greater will be the pressure. That's why this liquid goes the farthest. This hole here is throwing water, shooting water the farthest. So this happens simply because the weight of the liquid above, here increases with depth, thereby exerting more force, pushing the water out with greater force. That's very, very important to note. So this is property number 1 for 1 mark. All right, now let's take a different container. Let's suppose we have a different container. It has a whole ball or cylinder with many small holes all around it. Suppose we have a container like this. Suppose we have a cylinder like this, which has many holes all around it. All right, so let's suppose we have a hole like this with many holes all around it. Not only three on one side, but many holes are all around it. All right, suppose we have this. All right, so suppose that we have a container like this one. All right, so if we place this container or dip it in a bucket of water. Suppose we have a bucket that has water in it. Suppose this is a bucket of water. All right, so if you push this, suppose you push this way inside the water, you'll observe that water is going to be coming out in different directions with equal force. With equal force. So when this container is pushed into the bucket which has water in it, water will be seen to spout out from the different holes on the cylinder. What does this tell you? It means that liquid pressure is acting equally in all directions. This way, this way, this way, this way, this way, this way, and that. So this means that at any given time, at a given depth, liquid pressure pushes with the same strength in every direction, sideways, upwards, and downwards. This is why objects submerged in water feel pressure all around them, because pressure acts equally in all directions. Liquid pressure acts equally in all directions. So if you say this correctly, you have 2 marks there. Welcome, let us explain how heating silicon enables it to conduct electricity. This is about the band theory. Remember that silicon is a semiconductor material, meaning that its conductivity lies between that of metals and nonmetals. And in order to enhance its conductivity, it is either heated or it is doped, meaning some impurities need to be added to it. Then it becomes a better conductor. So explain how heating silicon enables it to conduct electricity. The material called silicon is a semiconductor. It has three layers. It has three layers. It has a layer called conduction band. First of all, what is called the valence band, valence. This is the valence band. The valence band this one here, and then it has another region which is called the conduction band, which is up here. Allow me to just call it CB, conduction band. Between the valence band and the conduction band, there's a gap, this gap here. It is called the forbidden gap. So, in order for it to conduct, electrons must migrate. The valence band is similar to the outer shell electrons. So for electrons to conduct, for a material to conduct, electrons must jump from here through the forbidden gap to the conduction gap. Now this gap is so wide that at the room temperature, electrons cannot move from here to there. In order to get the electrons to move from here to that end, to the conduction band, energy is needed. So that energy can be heat energy, which would cause the electrons in the valence band to gain kinetic energy, enough energy for them to jump this gap to there, so that they are available as free electrons to conduct. Welcome, learners. So 3 marks requires you to explain or to say that when silicon is heated, more electrons gain kinetic energy. This energy is kinetic energy, they are particles. Enough to jump from the valence band to the conduction band. That's 1 mark. So the heat energy will cause them to gain energy, kinetic energy to jump through the forbidden gap to the conduction band. So this process creates free electrons and holes, which act as charge carriers. So it will create free electrons. When the electrons jump from the valence band to the conduction band, they are going to be so free to conduct when such a material is connected to a circuit and a voltage is supplied. So the electrons and the holes become the charge carriers. By the way, holes are formed when electrons have left the valence band. So the places left by the gaps, the vacancies left by electrons once they have jumped from valence band to conduction band are called holes. They are positive in nature. So these are the two charge carriers. So with more carriers available, with as many electrons and holes available, silicon's ability to conduct electricity improves very significantly. 3 marks for saying these points. Briefly explain how a piece of iron can be magnetized by stroking. All right? Stroking means touching or heating. There are different ways you can turn a piece of iron into a magnet. One of them is stroking. Stroking is of two types. We have single stroke and double stroke. You can also use electricity to make what is known as an electromagnet, a temporary magnet. Welcome, learners. All right, so the setup is simple. All you have to do is place your piece of steel on a flat surface. And then you get a magnet, a non-magnet, with two poles, north and south. So this is a magnet. And then this one is your metal, which is iron, to be magnetized or to be turned into a magnet. So that's the setup. So 3 marks require you not to draw a diagram like that. I was just doing this to illustrate the point. All right. So you place the steel needle on a bench like this. Then stroke the steel needle with a southpaw. All right, so this needs to be southpaw according to the description here. So we have southpaw here. Over here, let's have southpaw. This is southpaw, and then that's northpaw. So this end here must touch there. Stroke means hit. So stroke that end with your southpaw of a bar magnet. This is a magnet along the whole length of the needle. So hit, stroke this, let it touch and move it up to there. And keep repeating this, touching, 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 stroking. That's called stroking. So stroke the steel needle with the south pole of the magnet along the whole length of the steel needle. Here, mind you, this is steel needle. I think the question is talking about steel needle. Here we are talking about just a piece of iron, but needles are made up of iron anyway. So by saying this one mark, so one at the end lifts the magnet well away from the steel needle, make a wide sweep, meaning this south pole must go all along the whole length a number of times. So you repeat the process several times, at the end of which you test if indeed a magnet has been created. How do you test? By simply bringing this magnet, the newly made magnet, closer to a non-magnet. Let's say you bring the north pole of the magnet to one of the ends. If this is repelled, then it means the magnet has been magnetized. The iron has been magnetized. If it is just attracted without being repelled, then that's not a sure way to tell that a magnet has been made. Remember that repulsion is the only test for a magnet. The only way to be sure that the other material has become a magnet is when it repels the actual magnet. And you will also tell the poles, the polarities of the newly made magnet. Welcome, learners. My name is Mr. Loyola once again. Question number 3. Define the term internal resistance of a cell. I'm sure you know what a cell is. A cell is basically something that you call a battery, but it's not a battery anyway, because a battery constitutes different cells or cells joined together. This is the thing you put in a torch in order to provide the torch with energy to light. So one end is positive, the other end is negative. Right, so this contains materials, chemicals inside. By the way, inside it, there is a rod, which is called carbon rod. It's an electrode. It's a carbon rod. And besides the carbon rod, there are chemicals inside. There are chemicals, right? So these chemicals will make the cell resist or offer a resistance to the flow of current, to the current flowing through. Let's suppose you connect this to a bulb. Connect this to a bulb such that current flows through it. Current I. So as current is flowing through, it is being slowed down or paused by materials in the cell. These are materials, chemicals basically, chemicals. There is ammonium chloride there and other chemicals. So these chemicals offer a resistance or an opposition. So the resistance offered by these materials or chemicals is what is called internal resistance. So we define internal resistance in the following manner. Internal resistance is defined as the opposition to current flow within the cell itself caused by the chemicals and materials inside the battery. In this case, we are referring to a cell. So we cannot use battery to mean cell. I beg your pardon, learners. So this is cell. That's how you define internal resistance. Part B, a battery of EMF of 7.3 watts and the internal resistance of 0.3 ohms is connected in series with a resistor of resistance 9.5 ohms. If we are to put this in a diagram, it's going to look like this. So we have a battery. Remember, battery is like this. That's the battery. So this battery is connected to a resistor. Remember, resistor is something like this. Such that the battery itself has an internal resistance, R, small r, of 0.3. 0.3 ohms. And this is connected to another resistor, usually called the external resistor, in series of 9.5. ohms. But this battery is capable of giving us a voltage, a potential difference, or an EMF of 7.3. 7.3 watts. That's the scenario. That's what the diagram is telling us. I mean, the statement. So a battery, this one here, of 7.3 watts, and having internal resistance of 0.3 ohms, is connected in a series, meaning in the same path, as the resistor of resistance 9.5. So using this information, determine the current in the circuit. So when the switch is closed, determine the current. Suppose there's a switch somewhere. All right, so determine the current in the circuit. So to find the current, we use this information here. The EMF is given to us as 7.3. That's the voltage supplied. All right. And the internal resistance is of this cell, the battery is 0.3, while the external resistance is R, 9.5. So we are asked to calculate current. So to calculate current, we use the fact that the total resistance is simply 9.5 add 0.3. We are able to do that because we are told these are in series. So we have 9.8 ohms. So to calculate current, we shall use what is called Ohm's law. EMF E is simply equal to current multiplied by internal resistance add external resistance, capital R, such that E, well, making I the subject, current is going to be equal to E, which is the EMF divided by the total resistance, R plus R. That's what is happening here. So our E is 7.3. Our total resistance is 9.8. Dividing the 2 will give us 0.74 ampere. So current is 0.74. Current flowing through this circuit when the circuit is closed. Make sure you know this formula very well. By the way, this is just a Ohm's law. This is similar to voltage. So voltage is equal to current times resistance. So 2 marks. It will be up to the discretion of the examiner to allocate marks so that it is 2 marks if you have said all this properly. My name is Mr. Loyola. We are revising a paper from Loyola Jesuit Secondary School, all the way from Gasungu. Thank you very much to the teachers there who set up this very beautiful paper. I'm saying it's a very beautiful paper because it is testing key skills needed to pass MSc Physics. Question number 3, 2, calculate the lost votes. So lost votes is simply lost votes is simply equal to lost votes, the votes lost within the cell due to internal resistance given by the small v is simply equal to internal resistance multiplied by current. Multiplied by current. Take note, we are looking at the current passing through the circuit, which is the same as the current drawn from the cell, the battery, multiplied by the internal resistance R. So V is equal to IR. So to find that, we simply have to multiply the current that we found, which is 0.74 multiplied by 0.3. This is the voltage which seems to be lost. So the actual voltage or potential difference across the resistor will be the difference between this and the EMF, which was given. That is going to give us effective voltage. So the effective voltage is E minus lost volts. We said lost volts is this one here. So the lost volts 0.22 subtract from the EMF will give us 7.08 volts. This one is the voltage dropped at the external resistor. Question number 3C, I think. Is it 4 or 3? It's 3 actually. So explain how constructive wave interference occurs. All right, remember that interference is a combination of two or more waves, which can be constructive or destructive. It is constructive when two waves that are in phase add upon each other to produce a wave that has greater amplitude than any one of the two. This is called constructive interference. On the other hand, when two waves are not in phase, such that the crest of one wave meets the trough of the other wave, these two waves are going to cancel out to produce zero effect, So we are asked to describe this one here for 2 marks. Right, so when two waves overlap, so these two waves are going to overlap each other so that their crests coincide. To coincide means that the two crests are like this. So you have this wave coinciding with another one. The result is going to be a wave that has a bigger amplitude, like this. All right, so these two waves are said to be in phase. All right, so when they are in phase like this, their effect is construction of a bigger wave. That's why they're called constructive wave interference. So the displacement, which is this, of the two, this one here, the displacement of this wave and this one here are going to combine to produce a resultant wave, this one, with greater amplitude than either of the individual waves. Welcome, learners. My name is Mr. Loyola once again. Welcome to the platform. Subscribe to the channel so that you don't miss anything that we upload in future. Welcome, learners. Number 4. Figure below is a diagram showing a permanent magnet. So this is a permanent magnet with north and south poles. It's a permanent bar magnet. Permanent bar magnet. So this is being moved towards a coil. So this magnet is being moved towards a coil. This is a coil, right? Remember this setup will produce a voltage which is called EMF, induced EMF, which can be observed using this center zero galvanometer. All right, it's going to be seen to deflect as this is being moved this way. This is going to deflect this way to oppose that, and when it is moved backwards, it will be seen to move this way to oppose this motion. So the question is, as current is being induced in the coil, moving the magnet into the coil will induce current. What type of polarity is formed at Y, this point here, of the coil? So for us to determine the polarity, by the way, refers to either north or south pole. So we need to determine the polarity there. So to do that, we shall need to apply what is called Lenz's law. Lenz's law states that the induced current always flows in a direction that opposes the change causing it. Make sure you are able to state the law. They are going to ask you state Lenz's law of electromagnetic induction. So you say the induced current always flows in a direction which opposes the change producing it. So with that on our mind, as the north pole of the magnet, as this pole is approaching the coil is going to develop a polarity that repels the approaching pole here. So this is going to develop a polarity to oppose this one, to repel this. So this is going to be north pole. So therefore, that's north pole. So therefore, Y of the coil becomes north pole to oppose the incoming north pole of the magnet. If this is south, this will become south as well. But as it is, this is north, that means this is going to be north pole. And of course, by default, this is going to be south pole. Welcome, learners. My name is Mr. Loyola, your teacher. Welcome to the platform. If you have any questions, don't hesitate to reach out. Using the numbers that we shared before. Welcome, learners, once again. 4b, explain how to determine the direction of the induced current in a coil when a magnet moves into the coil. How do you decide the direction of the induced current? Once again, you shall use Lenz's law. So the induced current always flows in a direction that opposes the motion of the magnet. I mentioned earlier on that you should be able to explain, or rather to state, the Lenz's law. All right. So the direction of the induced electric current is always such that it creates a magnetic field which opposes the change in the magnetic flux of the motion produced by it. So in simple words, nature hates change. All right. Nature always hates change. So if something changes the magnetic field or moves a magnet near a coil, the current flows in the direction that tries to stop that change or motion. All right. For example, when a magnet moves towards or away a magnet, a coil, sorry. So is the magnet, if the magnet is not moving towards the coil, the magnetic field always coil in increasing. So the magnetic field through the coil is increasing. So in this case, the direction of the magnet with respect to the coil will determine, can be used to determine the direction of current as well. So just say a use of Lenz's law in case you want to state that to support your mark to get your 1 mark. So the induced current always flows in a direction that opposes the motion of the magnet. Right, so observe the direction of the magnet, then current will move in a direction that is opposite to that. Another one is to apply Fleming's right-hand rule. Remember, Fleming's right-hand rule states that when the thumb, the forefinger, and the middle finger are held at 90 degrees with each other, the thumb represents the motion of the magnet, and the forefinger represents the magnetic field, while the middle finger represents the direction of the induced current. These are the responses that were sought after there. Explain why a gas bubble released at the bottom of the lake grows in size as it rises to the surface of the lake. All right, let's suppose that we have a surface of the lake. We have a lake. Suppose this is a lake, all right, with water in it. Of course, you'd expect the lake to have water in it. And then we have a bubble here down. The question is saying, why is it that the bubble as it is released from the bottom, its size becomes smaller? Sorry, its size becomes bigger. Why? One thing that you need to recall is that pressure, liquid pressure here at the bottom is bigger than the pressure on top. The high pressure here at the bottom will actually compress the bubble such that it gets smaller, or it shrinks if you like. But once it is released, the pressure of the lake due to the water in it is going to decrease. In so doing, the bubble is going to push outwards and get bigger again until it reaches the surface there. So 3 marks. What do they want you to do? It's not to draw, but to explain. All right, so pressure is high at the bottom of the lake, making the bubble small. 1 mark. And then as the bubble rises, pressure decreases. Another mark. And then finally, you will say lower pressure lets the bubble expand. Hence, the bubble grows bigger. 3 marks altogether. Welcome, learners. My name is Mr. Loyola, your teacher on this platform. Let's be together up to the end of the paper. It's a 13-question paper, and we are just around question number 4. Welcome to question number 5. Pay attention. A convex lens produces a real image of an object, and the image is 3 times the size of the object. The distance between the object and the image is 80 centimeters. Calculate the focal length of the lens. So just to put this in context, we have a lens, convex lens. Remember, a convex lens is shaped like this. All right. So let's say an object is over here. Let's suppose that our object is this one. All right, so remember, for an image to be formed, parallel rays that are parallel from the principal axis. This is your principal axis, by the way. Will be refracted upon reaching the lens. This is the lens. So the distance from the principal focus to the center of the lens is what is called the focal length, this one. The image such that the image is formed over here. And we are told it's a real image. If it's a real image, it means it's upside down. The distance from the object, so this is our object. This one here is the image. The distance from the object to the center of the lens is object distance, u. While the distance from the image to the center of the lens is the image distance, v. I think roughly this is the situation. Although the image doesn't really look magnified with respect to my object here, the object looks bigger than the image here, contrary to what the question is saying. All right, so that's just an illustration anyway. I hope you are good with it. So the distance between the object and the image is 80 centimeters. Calculate the focal length. So in order to find the focal length, let's use the fact that magnification, I beg your pardon, it's not magnesium. What am I thinking, by the way? All right, so the fact that the image size is 3 times the size of the object, it means that the magnification of this image is 3. Remember, magnification is the number of times the image is compared to the object. So magnification, which is image distance divided by object distance, is equal to 3. Make sure you understand this mathematics. It's important that you do. So we are saying magnification, M, is equal to image distance divided by object distance, but M is 3, so making V the subject, shall need to multiply U by 3. So V therefore is going to be equal to 3U. In other words, the image distance is 3 times the object distance. Welcome, learners. So we have this. But we are also told that the distance between the image and the object is 80. Which means V plus U is 80. Centimeters. This is just mathematics. Right, but V is 3U from the definition of magnification. We bring it here. It will give us 3U plus U. 3U plus U is equal to 80. Adding up 3U and U is 4U. So we have 4U is equal to 80, which means that U is equal to, sorry, this must be U. The object distance is going to be equal to 80 divided by 4. 80 divided by 4, which is 20. This one here. So now that we know U as 20, but V is equal to 3U. From there, so it will be 3 times 20, which is 60 centimeters. So we have our U is equal to 20, and our V is 60. So we need to find F, the focal length F. For us to do that, we shall make use of the length formula. F, the fork length, is equal to 1 over V. I'm sure you know this formula very well. Plus 1 over U. So V is 60. U is 20. So adding this, by the way, this is supposed to be 1 over F. So adding and simplifying will give you the value of F, the fork length, as 15. Just go through the calculation and convince yourself that you can find F using these equations. Welcome, learners. Part B, explain how the length of an inclined plane affects its mechanical advantage. An inclined plane, by the way, is a simple machine. It's something like this. Let's suppose that you are trying to get something, an object, to a certain height, h. A certain height, h. The object, such as a heavy load, this one, to be moved up to that point. It's easier to move this body through a plane. So this is called inclined plane. Inclined means it's arranged at an angle here. There's an angle there which is called the angle of inclination. There's an angle here known as angle of inclination. So that's why we call this an inclined plane. To incline means to lie in such a way that the plane is at an angle, usually acute angle, with the horizontal. All right, so as this body is being pulled up, you are applying a force called effort, usually denoted by the letter E. And this is to be moved along the distance D until it is brought somewhere there. So we are saying it's easier to pull the box. By the way, the box has a weight which is called the load. So the ease with which the load is moved from where it is by applying or pulling it using a force E to the top there will depend on a number of factors. One of them is the length of the incline, the length of the plane, the length of this thing here, this distance. How will that affect its mechanical advantage? So mechanical advantage simply tells you how much this is going to help you lift or move the box, the load. It represents how many times the machine, this thing, will multiply your effort. Simple. Will multiply your force. That's what mechanical advantage is. Usually calculated by dividing the load. Mechanical advantage is basically the load. MA is the load, which is the weight, divided by the force which you are exerting to pull it. So, in your opinion, what do you think? If we make this longer, let's say we have it up to there, how will it affect the size of the force which you must apply to pull it? Do you think you are going to need to require more force? Do you think you will need more force here to pull this one along a length like this to that point than you would require a force to move this to the same position? Where would you need more force? Where is more effort required? All right. So experiments have shown that when the length of the incline increases, the effort required becomes less. So the E becomes less. If you keep the load, which is the weight constant, you end up having greater mechanical advantage, meaning that it's easier for you to move the load along a long distance. Although the work done is going to be greater since there is more distance here, force times distance becomes bigger, but it's going to be easier to move this load through the distance to that point when the length is increased. Welcome, learners. So we are saying if you increase the length of the inclined plane, mechanical advantage becomes larger, meaning that less force is going to be needed to move the load. So the greater the length, the greater the mechanical advantage. You will say that here for 1 mark. When length of inclined plane increases, mechanical advantage increases, meaning there's going to be less effort to move the load. Conversely, if you decrease the length of the inclined plane, mechanical advantage becomes smaller, meaning you need more force to move the load. So 2 points, 2 marks. That's what you need to say here. But see, figure 3 shows a detector of radiation. In this case, we are talking about nuclear radiation. There are different ways of detecting nuclear radiation. How can you tell there's radiation or background radiation? Nuclear radiation can be detected using different machines or equipment. You can use what is called the centration counter. The centration counter, you can use the GM cube, the GM cube. You can use the Goodleaf electroscope. And you can also use this thing here, which we are asked to identify, meaning you must name this. So before you name, you must look at the structure. The structure will help you to tell what it is. So we have a base here, removable base placed there. Then we have the solid dry ice and a source of radiation over there, a lid, and fat rings like that. So from the structure, you can see this must be what is called cloud chamber. So cloud chamber, 1 mark. By saying cloud chamber, you have 1 mark. In particular, it's called diffusion cloud chamber. Diffusion cloud chamber. How does the instrument work to measure presence of radiation? How do you use this to tell the presence of radiation? All right, so the principle on which this works is basically ionization. Inside here, you can see the solid dry ice. Dry ice is basically frozen carbon dioxide. When the carbon dioxide is frozen, it is called dry ice. It's used here. Because you'll be wondering to say, how can ice be dry instead of being wet? It's not the water ice, no. It's basically frozen carbon dioxide. So solid dry ice cools the chamber, cools this chamber, cools it. This creates a layer of cold supersaturated vapor inside. So the vapor inside is cooled, becomes very cold and supersaturated. By saying this 1 mark, then ionization radiation passing through the vapor is going to knock off electrons from the atoms of the vapor. This is going to form a trail of charged ions. When the vapor inside is cooled and ionized, it's going to form trails such as this. One would be able to observe this. When they're dense like this, means that the radiation being detected is alpha. But when the trails are wavy like this, then that's going to represent beta radiation. It means beta detected. Whereas just inconsistent tracks like these will imply the presence of gamma. This will be seen inside here due to ionization. And most importantly, this is suitable ways of detecting alpha radiation, which is more most ionizing. So ionizing radiation passing through knocks electrons of the atoms, forming a trail of the charged ions. So this is a trail, these are trails of charged ions, right? So the vapor condenses. The vapor is going to condense around these ions, creating visible tracks. These visible tracks that show the path and presence of radiation. So 3 marks. Make sure you know how to explain this. Let me also ask you to go through your notes to revise how the other machines can be used. The other instruments can be used, such as the GM cube, for example. The examiner can this time decide to ask you to explain the working of the GM cube. We'll also revisit the notes on the working of the scintillation counter, another way of detecting radiation, and also look up for the use of the color electroscope, among others. Welcome, learners. Welcome to question number 6. We are making progress. This is question number 6. Remember, we are doing a 2-hour paper. We are taking our time to make sure that students understand the logic behind each question. Remember, it's not a matter of just passing through. We need to make sense out of each of the questions. Learners, my name is Mr. Loyola once again. All right, so this shows a circuit with some electronic device in use. So we have this device here, which is M, and another device here, P. And then we have 2 resistors, R1 and R2, and then we have a bulb there, and the battery. Very, very important. Have a look at the diagram closely before you proceed. So we are asked to name the device M and P. So M is basically, we recall this is the light dependent resistor. light dependent resistor, and P is a device called the transistor. All right. So explain how part P, which is the transistor, operates as a light operated switch in the circuit during a bright day, bright light. All right, you need to understand, candidates need to understand these things. The base here, then collector and the emitter. How does the current flow through this? All right, so current flows through, by the way, the transistor works as a switch. That's what we are asked to describe here. So in the first place, in a bright day, when light falls on the device M, which is the light dependent resistor, its resistance decreases. In other words, its opposition to the flow of current decreases. Remember, current and the resistance vary inversely. When the resistance is high, current is low, and the opposite is true. When resistance is low, current is high. So this is going to reduce when light falls on it. On a bright day, resistance is going to decrease. So this will make the voltage across resistor 2, this one, high. The voltage here will be high so that a large enough current or voltage is applied to the base over here. First, resistance of the LDR must decrease. That will lead to an increase in the voltage across resistor 2. So much so that a large enough voltage is applied to the base of the transistor. The base is this part here. So then the transistor switches on. The base, the function of the base is basically to control how much current flows from the collector. How much current flows from the collector to the emitter. That's the use of the base. But to do that, voltage is needed. So the transistor switches on, allowing current to flow from the collector to the emitter. Please take note of the direction of current. Current is from the collector to the emitter, like that, like this. The base simply acts as a controller of how much current needs to flow from the collector, that end, to the emitter. In so doing, it acts as a closed switch. It acts as a closed switch and activating the current, the component. In this case, it will activate the bulb to light. So current then will flow all the way to the negative terminal of the battery, then all the way like that, then activate the bulb there. to enable the bulb to light. Very important. Many candidates miss the point of the direction of current. So first of all, light needs to fall on the resistor there. This resistance is going to decrease. When the resistance decreases, current is going to flow through it. The current is going to be higher. All right, so the voltage across R2 is going to be higher. That voltage is going to be large enough to open, to turn on the switch, the transistor. The use of the transistor is to calculate how much current needs to flow from that end to the collector. Then it flows along up to the negative terminal of the battery, like that, enabling the bulb to give light. All right. So that's 3 marks. That's what you'd say in this particular case. Calculate the height of a water column which exerts its base, the pressure of 70 centimeters column of mercury. The situation here is like this. We have a column of mercury. Let's say this is mercury. Mercury is Hg. Mercury is Hg. Here's a column, or let's say height of 70 centimeters. And then above it, there's a column of water. Let's say this is water. Of height h. For the time being, let's just go hw. We don't know it. But we are told h of mercury is 70. We are also told the density of mercury, let's call density of mercury rho m, and the density of water as a rho w. So this is the situation we have. And rho w is 1 gram per cubic centimeter, while the density of mercury is 13,600 or 13.6 grams. So this is 13.6 grams. Per cubic centimeter. So this is the setup. So we are asked to calculate HW from this scenario here. Once again, this is the height of the water column. Then the density of water is 1 gram per cubic centimeter. Okay, and the height of the mercury column is 7 centimeters, while its density is 13. This is the only data we have. So we are asked to find the HW. All right, so to produce, rather to calculate the height of the liquid, of the water there, let's look at the definition of liquid pressure. Liquid pressure is simply the height multiplied by the density of the liquid multiplied by acceleration due to gravity, g. So the two pressures, the pressure due to the water and the pressure due to the mercury are equal. So equating these two, this is the height of the water column multiplied by the density of water multiplied by G is equal to the height of the mercury column multiplied by the density of mercury multiplied by G. So equate this. You see G is common on both sides, so you cancel that. You shall have height of the water multiplied by the pressure, the density of the water is equal to the height of the mercury multiplied by the density of the mercury, equating the two. We have cancelled out the G. This G is appearing on both sides and they are equal. So you can cancel them out. So we have this one here remaining. So the rest we just substitute. Do we know the value of HW? No, that's the one to calculate. But at least we know the density is 1 gram per cubic centimeter. So we bring it here. The height of the mercury is, do we know? Yes, we do, is 70 centimeters. And then the density of it is also known is 13.6 grams per cubic centimeter. So solving this equation will give us, substituting, we are substituting, just make HW the subject. So we divide both sides by the density of water, this one here, and then substitute, it shall give us the height equal to 952. Welcome, learners. My name is Mr. Loyola once again. Consider subscribing to the channel so that every time we upload a new video lesson, you become the first one to know. Construct a resistor, a fixed resistor, using the resistor code color codes with the value 25 kilo ohms. 25 kilo means 25,000. Remember, kilo means thousand. There's 25 with 3 zeros. Ohms. Then plus or minus 10%. That's what this is. Remember, the 10% is called tolerance. So that's what one needs to do in order to be able to convert this into color codes. That's what we are asked. Just have to arrange the colors in order. So the first one is the number 2. This 2 here is red. Okay, by the way, let me remind you. The color codes. All right, so remember that they are basically 10 colors. And each color has a value. Starting with black has a value of 0. And then brown has a value of 1. Red has a value of 2. Make sure you know these things. Orange has a value of 3. The yellow has a value of 4. The green is 5. Green is 5. Well, blue is 6. Blue is 6. And violet is 7. Violet is 7. And gray is 8. Make sure you know these colors. Gray is 8. And white is 9. These are called color codes. So you can use these to calculate resistance. Given the color codes on a resistor, we can calculate resistance, or given the value of the resistance, we can convert into color codes. So the easier way to remember this is to use a mnemonic device. Bad boys race our young girls, but Violet generally wins. So Violet is a clever girl, eh? All right, so bad boys race our young girls, but Violet generally wins. So that's from 0 to 9, not from 1 to 9. We start from 0 then to 9. That's why they said there are 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7 colors. And then we have additional colors such as gold and silver, which in most cases gives this is the basis for calculating color codes. So the first digit, usually the first color on a resistor represents the value. The second color also represents a given value, while the third one represents the number of zeros. These rules are supposed to be known for you to handle color codes. Right, so 25,000 ohms, once again, I don't know what happened. I wrote it somewhere, this thing. So we have 25,000 kilo, because of kilo, ohms plus and minus 10%. Right, so that's what we have. So construct a fixed resistor using resistor color codes with the value of 25 kilo ohms. So the resistor color code for 25,000 ohms plus or minus 10%. The first number is a 2, this 2 here. That means it's red. The first code is red. So we have, this is our resistor. So the first code is red. The second is a 5. That means it's green. It means use the exact color. So we have red, green. This is red. The third one is equal to the number of zeros. There are 3 zeros. So that means the third band is an orange. Remember, the third band represents the number of zeros, and there are 3 zeros here. That means it's orange. Orange gives us the number of zeros. The same orange is this one here. I confuse a lot with yellow. And then the last one, which is the 10% tolerance, the silver. So look for silver. Not sure which one is silver. There's no silver here actually. All right, there isn't silver. So silver comes at the end there for tolerance. So this is the resistance that's needed. So the color, the final code is going to be red, green, orange, and then silver. The last one is silver, which is the 10%. Gold, I think, is 20%. Just verify to be sure. So silver is 10%, gold is 20%, gold is 5%. If there's no color after after this third one, then it means it's 20%. Welcome, learners. My name is Mr. Loyola once again. Part B. Explain briefly how water behaves as temperature decreases from 4 degrees Celsius to 0 degrees Celsius. Remember that water behaves anomalously or strangely in that when you are cooling it from 4 degrees Celsius, which is higher than 0, its volume tends to increase. In other words, it expands instead of contracting like other substances do. So what you need to do here is describe the anomalous expansion of water. So from 4 degrees Celsius to 0, water expands. That's what they want you to say here, 2 marks. Instead of contracting, its volume increases and its density decreases. Remember that volume and the density are inversely proportional to one another. If you go back to the formula, density is equal to mass divided by volume. So in most cases, we are looking at a fixed mass of water, like mass of water is constant. Fixed mass of water. When you cool it, the volume increases such that you end up dividing a constant mass by a large volume will produce a smaller density. So density decreases. In other words, density and volume vary inversely with each other. Okay, so your response, therefore 2 marks, must include these facts. So from 4 degrees Celsius, when cooled from 4 degrees Celsius to 0 degrees Celsius, water expands behavior. Water expands instead of contracting. 1 mark. Its volume increases and its density decreases. Another mark, like 2 marks altogether. A board of mass 400 grams tied to a string is rotated in horizontal cycle of radius 1.2 meters at 2 hertz frequency. You need to identify what these are. This is mass in kilograms, it's just 0.4. Divide this by 1000. This is radius, and that's frequency. Calculate the tension developed in the string. So the scenario we have is we have a string to which a body is attached. This body has a mass of 0.4 kilograms, 0.4 kgs, which is the same as 400. So this is being moved in a circular path like that. So as it is being moved, a force is developed which is called tension, and this tension is equal to what is called centripetal force, Fc. All right, so in other words, in order to calculate the tension, we are as good as being asked to calculate centripetal force. Remember, centripetal force is the center-seeking force, the force which is needed to keep the body moving towards the center of the circle. So in this case, we shall need simply to use, first of all, to find what is called angular velocity. Angular velocity is 2 pi times frequency. So 2 pi times frequency, which is 2 times pi, that's 2 pi times 2 is 4 radians per second. That's angular velocity. And using Newton's second law of motion, force is equal to ma, for which a, which is acceleration, also known as angular acceleration, is the square of the velocity multiplied by r. This one, omega, is the angular velocity. So we know m is 0.4 kgs. Angular velocity is what we just calculated here. And the radius is 1.2. So multiplying through shall give us centripetal force of 75.8 newtons. And that's equal to our tension. Welcome, learners. My name is Mr. Paul Loyola, your teacher. Invite your friends to join us on this platform so that they too can benefit from us. Question number 7, figure below is a diagram, is a graph of force against the extension. So we have force along the y-axis and extension along the x-axis. Describe the extension of the spring as illustrated. What's happening to the extension of the spring as illustrated by the graph? So you need to know what these things are. This is the origin. When no force is exerted, the extension is 0. When force is exerted, initially they graph the material. The spring increases in length proportional to the force. In other words, the spring obeys what is called Hooke's law. But when more force is exerted on it, it stretches in a manner that it does not obey Hooke's law anymore. Remember Hooke's law? Hooke's law says extension is directly proportional to the force on the spring. So the first part presents that direct relationship of force and extension. But from A to B, the spring begins to behave otherwise. The extension is not proportionate to the force anymore until a certain point, beyond which, with the point known as the yield point, this is the yield point, beyond which the spring now gets damaged completely. So 3 marks, what are the 3 marks for? So from O to A, from here to there, where the graph looks a bit straight, extension increases proportionally with force, meaning that extension is directly proportional to the force applied, obeying Hooke's law. That's 1 mark. How do we know that? This part here is straight line. And then beyond A, extension increases faster. Extension increases much faster than the force applied. And in that case, proportionality is no longer obeyed. So Hooke's law is lost here, beyond this point, because the graph is no longer a straight line. And then at B over here, and beyond that, the spring is stretched permanently, and it will no longer return to its original length. These are the 3 points that we need to have to obtain from this graph line here. Welcome, learners. My name is Mr. Loyola, your teacher. Welcome. Invite your friends wherever they are. This is Loyola Jesuit Secondary School, one of the best schools in the country. This is a privilege for us to work on a mock paper from such a school. It's a high reputation school, and its mock papers are of high quality, I must say that. Using this value we found here, find the friction or average frictional force, the force that caused it to stop. When it stops, it means that the engine force is equal to the frictional force. So here it's as good as finding the engine force as it is stopping. So we shall use Newton's second law of motion, this one. Acceleration is directly proportional to force when mass is constant. F is equal to ma. So m is 500 kgs, we are told. A is 400, A is 4 meters per second square. So multiplying 5 by 4 will give us 2000 newtons. So F is equal to 2000 newtons. Welcome, learners. My name is Mr. Loyola once again. Number 8, state the principle of conservation of mechanical advantage. Without wasting your time, the principle of conservation of mechanical energy. Sorry, why did I say mechanical advantage? This is mechanical energy. Mechanical energy, remember, is kinetic energy plus potential energy. So it states that the total kinetic and potential energy stays the same, stays constant if no external forces act. In other words, if no external forces act on a body, the total kinetic energy and potential energy are constant, stays the same. That's 1 mark. This is like the law of energy conservation, which says that energy is neither gained nor lost. Sorry, forgive me. Energy is neither created nor destroyed, but it changes from one form to another, or is transferred from one form to another. But here we are talking about the potential energy and kinetic energy. Together they call mechanical energy. So total kinetic and potential energy stays constant if no external forces act on it. Welcome, learners. My name is Mr. Loyola, your teacher. A gas occupies a volume of 2 cubic meters when its pressure is 1040 millimeters of mercury and its temperature is 27 degrees Celsius. What volume would it occupy at standard temperature and pressure? Welcome, learners. It is important for us to identify the variables that we are given. So this one is initial volume, we'll call it V1. And this over here is initial pressure, call it P1. And 27 degrees is initial temperature. We are asked to calculate its volume. In other words, final volume, V2, that would be occupied at standard temperature and the pressure. So this is T2. And this over here, final pressure, call it P2. So final temperature T2. Right, so we are asked to calculate, we know V1, we know P1, we know T1, we know T2, and we know P2. So these are known. We know these variables. So what we need now is to calculate V2. All right, so that's what we have. Think about this question. What needs to be done? So standard pressure is 760 millimeters of mercury, while standard temperature is 0 degrees Celsius. So we are going to borrow a very useful law, which is called the combined gas law. The combined gas law says that the product of the initial pressure and initial volume divided by the initial temperature is equal to the final pressure times final volume divided by final temperature. This is very powerful equation we need. And this holds when the temperatures are in absolute temperature in terms of absolute temperature scale, kelvins. So convert the temperatures to Kelvin. Remember, just add you just add 273 to each of the temperatures. So 27 add 273, you have 300. 0 add 273, you have 273. So all you have to do now is to substitute these values into the equation and calculate V2. This one. So that shouldn't be an issue. Solve the equation to find V2. So V2, which is the final volume, will be 2.73 cubic meters. Welcome, learners. Part C of that question, explain mutual induction. Explain mutual induction. I'm sure you recall that mutual induction is basically the process where a change in the current flowing through one coil creates or induces an automatic electromotive force, EMF, or voltage in a nearby separate coil due to the magnetic field linking between the two of them. The setup for this is simply, suppose we have a coil. We have a coil. Such as this. My diagram is just sketchy. We have two coils that are placed side by side. So we have coil A and coil B placed close to each other. And here we have a magnet. So when the magnet is moved into the first coil, which is A, it is going to induce an EMF or a current through it. That EMF is going to induce yet another EMF in coil B. And you can see this as the magnet is moved in and out of the coil. As the magnet moves in and out of coil A, an EMF is going to be induced. All right, so this is called mutual induction. So the current induced here will also induce an EMF in B. So this is a process. Mutual induction is a process whereby a change in current flowing through one coil will create or induce an EMF or an electromotive force, which is voltage, in a nearby separate coil due to the magnetic field linking between the two. So there is a magnetic field linking between these two that will create an EM there. Mutual means two. If you and me have something to do with each other, then there's a mutual agreement between the two of us. So explain the mutual mutual induction. So mutual induction occurs when change in current in one coil produces a changing magnetic flux from a changing magnetic field linking those two coils. So occurs when a change in current in one coil produces a changing magnetic flux. So this flux links with the neighboring coil, the field, this one referring to the field. It's going to link with the neighboring coil like we showed in the diagram. As a result, this is going to induce EMF, which is a voltage in the second coil. 3 marks. Explain how an echo can be used to determine the depth of a sea. All right, let's suppose that we have a sea. Suppose we have a sea with water in it. And then we have a ship. We have a ship moving on it, moving on the sea, on the surface. Maybe let's say a little bit submerged. So there's need to determine how deep this sea is. D. This is a shape. Say this is a sea. So because this looks smaller than a sea has to look. All right. So how do we determine? Explain how an echo can be used to determine the depth, how deep this is. Remember that echo is a reflected sound. So how can sound from the ship be used to determine how deep this is? Okay. So that's the scenario. So in order to do that, a sound wave is sent from the ship traveling down to the seabed. A sound pulse or sound signal, pulse is just a signal, is sent from the ship traveling down to the seabed, to the bottom of the sea. Upon reaching there, the sound wave or pulse is going to be reflected off the seabed as an echo and goes back to the ship. So to calculate the depth, you simply take the speed of the sound in the water. The speed of sound in water is roughly around 1,500 meters per second, then multiplied by time taken for the echo to be heard, then divide by 2. So you're dividing by 2 because the distance is used, like the sound will go into the water to the bottom and back. It's two-way. So you divide by 2. So the distance can be found by simply taking the speed of sound multiplied by the time taken. By saying these 3 points, you have 3 marks. Welcome, learners. Welcome to question number 9. Figure 6 is a diagram showing waves on a rope XY. So this is a rope. It's being moved up and down, up and down, up and down, up and down to form these waves, which are transverse in nature. If the rope XY is swung from the word swing up and down 20 times in 2 seconds, calculate the average speed of the wave. So what information can we extract from the diagram? From the diagram here, we can extract from the statement, we can extract something. The rope is swung up and down 20 times in 2 seconds. This can help us to find the frequency. Remember, frequency is the number of oscillations. In this case, it's the number of swingings divided by time. So in this case, the number of swings is 20 of them divided by time, which is 2 seconds. The frequency is going to be 10 hertz. That's the first thing that you should have, one should see. So we have frequency there. In order to calculate speed, the speed is equal to frequency multiplied by wavelength. But do we know wavelength? No, we don't. We need to find it. All right, so wavelength can be found from the diagram. Remember, wavelength is the distance from here to there, or the distance between any 2 points which are in phase. It can be from here to this point, because these 2 points are in phase with each other. They're identical points, or you can also do the same here. Right. So let's find how many complete oscillations we have. We have 1, 2, 3, 4. Roughly. The question is asking us for average, so we don't have to worry about this last part and that first part over there. So there are 4 waves here, and all of them are covering a distance of 1.8. That means the distance between any 2 identical points is going to be 1.8 meters divided by 4. That's going to give us this guy here, which is the wavelength. All right, so that's what we have. So to calculate speed with those information given, number of waves is 4 of them, the 4 full cycles, and to find wavelengths, simply take the entire distance divided by 4. The 4 is the number of waves, complete waves, which is 0.45. And frequency is 10, which we already found. So to find speed, we take 10 multiplied by 0.45, which gives us 4.5 meters per second. Explain how a microwave screw gauge micrometer, I beg your pardon, why am I thinking about microwave? Explain how a micrometer screw gauge can be used to measure the thickness of a paper. Micrometer screw gauge, I'm sure you have seen one, whether be it in a diagram or the actual one in your lab. So we'll go straight to describe how it can be used. So first of all, you close the jaws of the micrometer screw gauge without paper on it. Then you check and record any zero errors. If there are any zero errors, check and record, and then you correct them later after measurement is carried out. Then open the jaws, place many sheets, identical sheets. One of them is the one you have to measure. Identical sheets of paper between the anvil and the spindle. Please go back to the diagram of the micrometer screw gauge and see which one is which one. Turn the ratchet until it slips. Gentle grip to ensure that it's gently the papers are gently gripped by this anvil and the spindle. And then thereafter read the main scale and the thimble scale. So you add these up to find the thickness of one sheet of paper. You simply divide the total reading by the number of sheets to get the thickness of one. 3 marks. In one particular experiment, we are getting towards the end. The mass of the trolley was kept constant. The time t for the trolley to move a distance of 1.0 meters from rest was determined for various values of the pulling force F. The acceleration was calculated using S, or distance, equals to 1 divided by 2at squared. A is acceleration, where S is 1. So the following values were obtained. So we have values of force and values of acceleration. Just quickly, if you look at the trend here, you see that as force increases, acceleration is also increasing. That means if we plot a graph of force against acceleration, we must get a straight line graph like this one here. I want to leave this to you as homework. Try to plot the values and tell me the shape of the graph that you are going to obtain. We will not plot it here. Question number 11. Figure 7 is a diagram of alternating current generator known as AC generator. Explain how an alternating current generator works. Explain how an alternating current generator works. You have to be on the watch out, on the lookout for questions like this. You may be asked to explain how a DC motor works. Make sure you know how the telephone receiver works. You may be asked to explain how the loudspeaker works. You know those things, eh? Or how does a transformer works? All right, so here we are looking at this generator here. First, you must know the structure. It has two magnets. Between them, there's a magnetic field or magnetic flux, and then a coil, which is made to rotate. And then we have parts like the carbon brushes and the load. The load is just a resistor or any material. And then we have slip rings. All right, explain how this works. So the coil rotates. This coil rotates between the poles of a magnet. It rotates. It goes up and down, up like that. Doesn't go in a continuous manner. No, it When one end goes up, the other end goes down. And the case when this goes up, this goes down. When this end goes up, this comes down. So in so doing, it cuts magnetic field lines, the lines between the two poles. So induced current flows directly, the direction reverses every half, meaning it goes up. When this goes up, this goes down. When this goes up, this comes down, and so on, due to the changing magnetic flux. So the induced current flows, direction reverses every half, turning due to changing magnetic flux. So the strip rings maintain contact. These things here maintain contact between the coil and the outside circuit to which the load is connected, delivering an alternating current to the external load. That's 3 marks. With the aid of a well-labeled diagram, describe how a mass of an object can be determined using the principle of moments. First of all, you should remember the principle of moments. What does the principle of moments state? The principle of moments states that the sum of the clockwise moments equals to the sum of the anti-clockwise moments. So using a well-labeled diagram, we need to use that principle to determine the mass, an unknown mass, the mass of an object. So the diagram that we need is this one here, consisting of a ruler, which is pivoted here, supported there. Roughly, this is supposed to be 50 centimeters. It's the middle. So on one end, an unknown mass is attached. On the other end, a known mass is attached, a standard mass. And the distance between the pivot and the unknown mass is d1, while the distance between the pivot and the known mass is d2. So how can we use this to determine the mass of unknown mass, unknown object? So you set up this apparatus as shown. This can be given 2 marks depending on the discretion of the examiner. So we suspend the uniform beam freely at its center. So support it at the center there so that it bounces horizontally at the point. This should be horizontal without mass attached to it. Next, you hang an object of unknown mass here on one side at a measured distance d1 from the pivot. So this is d1. You do the same. You hang a standard mass, m on the opposite side. Then adjust its distance d2 until the beam is horizontal again. So you move the mass, the standard mass, until the beam becomes horizontal again. Apply the principle of moments. What does the principle of moments state? The principle of moments states that clockwise moment is equal to anti-clockwise moment. So you write the expression here for the clockwise moment, which is this distance multiplied by the weight of this mass. Take note, we are saying the the weight. Okay, you can leave the weight to right. You can use masses. Yeah, because by definition, moment of a force is the product of the force, in this case weight, and the perpendicular distance. So apply the principle of moments. Clockwise moments will be mg times d1. Mg is the force, basically the weight, mg times d1. So the moment this side of the system. So this is equal to the moment, the other side. Mg is just weight. All right, so you can see a g is common. That means by the end of the day, you only have mass to deal with. So we divide both sides of the equation by d1. This must give us this equation, the final equation. So the mass, the non-mass is equal to the non-mass multiplied by d2 divided by d1. Welcome, learners. My name is Mr. Loyola once again. Question number 12, sorry. We are now approaching the end. Using a truth table, describe how a NAND gate works. NAND. By the way, a NAND gate, given by this symbol here, is a combination of two gates, the AND and a NOT. Remember, an AND gate is given by this symbol. This is an AND with two inputs. Call it A and B. And one input, output. Call it X. While a NOT is simply something like this. I think with one input producing one output. A NOT, it does the opposite. So when you enter one, when you input a 1 in a NOT, you produce the opposite. When you input a 0, you produce a 1. So when you combine these two, you have a NOT, an AND, forgive me with my diagrams, don't look nice. Combine this AND with a NOT, something like this. It means whatever the output of the AND gate here, let's call this the output, that is going to be an input for a NOT, which is going to be the opposite. Let's say L and B are inputs. Whatever the output is at X, that is going to be converted to something else by the NOT to produce a Y. That's why sometimes the NOT is referred to as an inverter, because it changes the inputs to something else. So instead of drawing this, we draw that symbol there. That's the symbol for a NOT, a NAND. So this is a NAND. That's a NAND gate. This is a NOT. It's a combination. A NAND is a combination of and NOT. In fact, NAND means not and. Welcome learners. So using a truth table is just a table of values, inputs and outputs. That's what, not something complicated. Right, so in this case, the truth table, I want you to understand this. Of course, this is quite a bit of higher order. Indeed, coming from a school like Loyola, I understand. But in most cases, you are asked the basic ones, the OR gate, AND gate, and like that, something like that. All right, so let's suppose that A and B are inputs, which are ones and zeros, as shown there. So assuming that this is an AND gate, when both of them are zero, the AND will give you a zero. But because we have put a note there, a note AND, means these zeros are going to be converted to ones, these ones. So it's 0 and 1 for an AND gate produces 0, and it produces a 1 for a NAND. Just take note that a NAND simply converts whatever the AND gate is producing. All right? When both A and B are ones, an AND is 1, but a NAND is going to invert that to a 0. Take note that a NAND becomes high when an AND gate is low, and becomes low when an AND gate is 1. Take note of that. So this is called the truth table for this kind of gate. So how does it operate? So a NAND gate, which is this whole thing, is a combination of an AND, this one, and a NOT gate. So it produces an output that is the opposite, which is not of the AND gate. That's why it's called NAND. NAND is short form of not AND. So from the truth table, the output Y is high for all input combinations except when both inputs are high, except here when both of them are high. But all of them will give you outputs which are high. So when A is 1, B is 1, the AND output is going to be a 1 here. But the AND is going to give us 0. Therefore, NAND gate gives 1 for combinations such as 0, 0, 0, 1, and 1, 0, but gives 1 for one situation. Welcome, learners. My name is Mr. Paul Chilola, your teacher. Remember, we are coming closer to the end of the paper. We have already had 3 hours doing this paper. I hope you are going to follow logically as you are reviewing this paper. I believe so. Question B, explain how P-type semiconductor can be produced using doping. What is doping? Doping is simply adding some impurities to a semiconductor, such as silicon or germanium. Doping. And in order to produce a P-type semiconductor, which is an extrinsic semiconductor, we need to dope the semiconductor with group 3 elements. So to add group 3 elements to the semiconductor. So you dope the semiconductor, which can be silicon or germanium. Remember, silicon and germanium belong to group number 4 of the periodic table. So each has 4 electrons in their outermost shell. All right, so you add small amounts of the group 3 elements. The most common one is boron. So boron is added to silicon, trying to bond, trying to make them bond. Boron has 3 electrons in its outer shell, while silicon has 4. So when trying to bond the two, there is what is called incomplete bonding. So each dopant is these chemicals, elements. Each dopant has only 3 valence electrons or outermost shell electrons. So leaving one bond unsatisfied. Look here, it's like silicon has a need, is hungry for 4 electrons in order to be bonded to something else. But what is available has only 3 electrons in the outermost shell. That means one space in silicon will remain vacant or unsatisfied. So the result of that is the formation of a vacancy, which is called a hole. That unsatisfied electron forms a vacancy. So the unsatisfied bond creates a vacancy, which is called a hole. This hole is not a literal hole, which you know. It's just a positive charge carrier. In this case, it behaves like a positive charge carrier, the hole. So effectively, it happens that the majority of the carriers become the holes, and they become more of them, and they outnumber the electrons, the free electrons. So by the end of the day, the semiconductor becomes predominantly positive. And the majority carriers, in this case, become the minority, sorry. The minority carriers become electrons because there are fewer of them. They are still there, but they are in much less numbers. As a result, it is the holes that are accountable for conduction. So this is how we make a semiconductor called P-type semiconductor using doping. So the process of adding these impurities to the pure semiconductor is called doping method. 5 marks. Thank God we have come to the end. This is question number 13. With the aid of a well-labeled diagram, describe the problem of short sight in human eye. Short sight, which is also called myopia, is when one is able to see objects that are closer but fail to see objects that are far away. So the diagram that they are looking for is this one here. This is the eye, and this lining here is the retina where images are formed. So an object that is far away cannot be seen by this individual because the rays of light upon refraction by the lenses are going to converge before they reaching the retina here. That's called short sight. Okay? Being able to see objects that are closer and not objects that are far. So in order to correct that, one has to wear glasses that have concave lenses. Concave lenses like this. So rays from a far object are immediately refracted before they are refracted by the lens. They're refracted by the the concave lens. Trying to delay the refraction by the main lens there. So this would cause the rays to go beyond where they initially were formed and they fall on the retina, enabling you to see objects that are far. So having drawn these diagrams, that can be 2 marks. We have 5 marks there. We need 3 more points to get 5 marks. So a short sight person is the situation whereby the eye fails to focus on a distance objects clearly because in most cases the eyeball is too long. The eyeball is too long for the rays from a distant object. So in this situation, the light rays converge before reaching the retina, like here. The rays fail to reach here because for one to see an object from far, the rays must touch here where they meet the sensitive cells, which are the cones and the rods. Right, so the problem can be corrected by placing a concave or diverging lens which can delay the meeting of the right rays, push them, extend them to the retina, enabling the person